In this video, we're going to begin to take a look at intermolecular forces. So there are three different types that we're going to take a look at. We're going to define them and look at some of the specifics that go with it. So before we get into intermolecular forces, I just want to review that intramolecular forces. So intra means within. These are bonds that are present between atoms within a molecule. So we've looked at this before in previous videos. And so ionic, polar covalent, and covalent are all types of bonds that are intramolecular forces. What we're specifically going to look at in this video are intermolecular forces. So these are forces of attraction between particles of a compound that holds it together in either the solid or the liquid state. And there are three types. So there's one's called dipole-dipole, one's called London forces, and one that you might already be familiar with called hydrogen bonding. Now, it's really important to keep in mind that intramolecular forces, or bonds, are definitely much greater in strength than intermolecular forces, so forces between molecules. That's not saying that intermolecular forces can't be strong, but they are not as strong as a bond, and they can be broken. I guess if you think of it in a way as breaking those forces between molecules, because that's how we then get melting or boiling of different substances and changes of state. Okay, so let's get into the three different types. The first type is dipole-dipole forces, and these are forces of attraction between polar molecules. So these are molecules that have an overall dipole. So something like HCl has a bond dipole that's pointing towards the chlorines. And so when two of these molecules come close together, the end that is partial negative on one molecule is going to be attracted to the end that has the partial positive charge on the other molecule. And so they are attracted together and create this intermolecular force holding those molecules together. Now, the strength is totally dependent on the polarity of the molecule. So the higher the polarity, the stronger the force of attraction is going to be. The second type is a little bit weirder. It's kind of also dependent on dipoles, but these are called London forces. They have many different names. They're also called London dispersion forces. They're also called temporary dipole forces, and they exist in all molecules, so both nonpolar and polar molecules. And so when two molecules come together, it's very possible that you get temporary dipoles that are arising just from the fact that these two molecules are coming together. So if you take something that's, say, nonpolar or neutrally charged, and you bring two molecules of it together, you can induce a charge on each end where the electrons are kind of shifting to one side, creating an end that's partially negative and partially positive, and then you get an attraction between those forces. Now, the big difference here from dipole-dipole forces is that these dipoles are temporary. They do not last very long, and they kind of come on and off depending on how close these molecules together and which way the electrons are shifting. So they exist in both nonpolar and polar molecules. Now, in terms of London forces, another definition we need is something called polarizability. So that's the ease of being able to distort the electron cloud by an electric field. So it's how easy is it to push these and distort these electrons to one side or the other. Now, in terms of how strong London forces are, there are a few factors that will affect how strong they are or the magnitude of the London forces. Those are the number of electrons, the size or the volume of the electron cloud, and the shape of the molecules. So let's look at each one individually. First, starting with the number of electrons, the greater the number of electrons, the larger the distance we have between the valence electrons and the nucleus. And so the attraction of the valence electrons to the nucleus is going to decrease because we're getting further away from the nucleus. And so we would say that it's polarized more easily. So if there are more electrons, the force or the magnitude of the London forces is greater. Looking at the size or the volume of the electron cloud, in a large electron cloud, the attraction of the electrons to the nucleus is not going to be as great as a small electron cloud. So what does that mean? Well, if you have a smaller molecule like C3H8 here, you can see the volume of that is much smaller than C8H18. And so electrons in this large electron cloud here are actually more easily polarized, and so it's going to have a greater magnitude of London forces. Finally, the shape of the molecule does matter as well. So London forces are greater when the surface area of a molecule is greater. So if you look at something like these two C5H12 molecules, the first one here, pentane, has a larger surface area. And so the London forces are going to be greater here than in this 2,2-dimethyl propane molecule because its surface area is much smaller. Now we have another term here called van der Waals or VDW forces. And they are defined as all of these different types of forces. So London forces and dipole-dipole forces are both considered to be part of van der Waals forces. There's also called something called dipole-induced dipole, and this is kind of a combination of London and dipole-dipole forces. So you'd have a dipole from one molecule, a permanent dipole from one molecule, inducing a temporary dipole on another molecule. Now, the last type of intermolecular force is hydrogen bonding. This is a special type of dipole-dipole attraction. And it is formally defined, and its definition is awful, but let's look at it here, as the attraction of hydrogen atoms that are bonded to a nitrogen, oxygen, or fluorine. And those hydrogen atoms are attracted to a lone pair of electrons on another nitrogen, oxygen, or fluorine in an adjacent molecule. So what the heck does this mean? Well, let's take a look at our pictures here. If we take a look at, for example, water, the oxygens have lone pairs of electrons on them. There's two pairs. And so our definition is saying that this hydrogen is attached to an oxygen. So that checks off the first sort of part here. And that is attracted to a lone pair of electrons on another oxygen on an adjacent molecule. So right here is where our hydrogen bond is. Now we call it a bond, but really it's a force of attraction. So looking at our second one with nitrogen here, we have a hydrogen that's attached to a nitrogen, and it's attracted to, in this case, it can be attracted to different molecules. So a lone pair of electrons on an oxygen on an adjacent atom. You could also have something like FH. These fluorines have lone pairs of electrons. So again, our definition, hydrogen attached to a fluorine, and it's attracted to a lone pair of electrons on another fluorine atom. Okay, so what you're looking for is that hydrogen attached to one of these three elements here, and you're looking for the attraction to a lone pair of electrons on one of those three atoms, again in an adjacent molecule. So those are the three types of intermolecular forces. That's it for this video. We'll see you in the next one.